see the working of P-channel enhancement type MOSFET, which is also known as PMOS. So this is its structure. We have N substrate and drain and source are made up of P plus type materials. And here we have the oxide layer, above that we have a metal layer. This is the gate terminal, this is source terminal, this is drain terminal, and at the bottom we have body terminal. And we know that our source is taken as reference, so the voltage of source is 0, that is the source is grounded. Now we will see what happens for different conditions of VGS and VDS. So for our first condition is that VGS is 0 and VDS is also 0. So if we don't apply any voltage at gate and also we don't apply any voltage at drain, then nothing will happen. So obviously our drain current will be 0, that is ID equals to 0. Now our second condition is that VGS is still 0 but VDS is negative. And we know that in enhancement type MOSFET we don't have the channel, we have to create it, and that channel can be found only if we apply some voltage at gate. And since our gate voltage is 0, so whatever voltage we apply at the drain, that doesn't matter. Our charge carriers won't be able to travel from the source to drain without the formation of channel. So again our ID will be 0 because current is the flow of charge carriers, and if charge carriers won't flow, then our ID will be 0. Third condition is that VGS is 0 but VDS is positive. Again our VGS is 0, so whatever our VDS is, that doesn't matter, our ID will be 0. Now we will see the fourth condition. So our fourth condition is that VGS is negative and VDS is also negative. VGS is negative but less in magnitude, and VDS is negative. So why we are applying VDS here negative? Because if we imagine our diode to be here, like it will be like this. Because in our diode, this is our P side and this is our N side, and since our drain is of P type material, so this P side will be here, and our substrate is of N type material, so N side will be here. So our diode will be here. This is an imaginary diode. So for this diode to be reverse biased, we know that we have to connect P side with negative terminal and N side with positive terminal. So we have to connect this P side with the negative terminal for reverse bias. So we need to have here negative terminal at the drain. Why we need this reverse bias? Because reverse bias will increase the depletion region. And this increase in depletion region will lead to creation of strong electric field. And due to this electric field, our charge carriers will flow. That is, our charge carriers will move, and charge carriers movement will lead to flow of ID. So we need reverse bias for the flow of ID, and for reverse bias we need to apply negative voltage at the drain. So what happens when we apply VGS negative and VDS negative? Let us see. Our source is 0, we know that. And if we apply negative voltage at gate, that is negative terminal and this will be positive terminal. So holes from this positive terminal will come into the N substrate. This is N substrate. And we know that N type material looks like positive ion paired with electrons, and there will be so many pairs. So these holes from this positive terminal will go into N substrate and they will recombine with these electrons. But when we apply less VGS, that is less negative VGS, we will just get few holes which will just recombine with the electrons of the N substrate. They won't be able to form any channel. So what is happening here? Holes from the positive terminal go into N substrate and recombine with the electrons of N substrate, and no channel is formed. And if we keep on increasing this VGS in the negative direction, that if we make our VGS more and more negative, then we will have more and more holes from this positive terminal, and those extra holes left will be able to form the channel here. So let us remove this and let us see what happens when we keep on increasing the VGS in the negative direction. So now it is condition 5 and it is not less. Our holes will form here the channel. So when our VGS is negative but it is not less in magnitude, it will form the channel. Like here, all the electron of N substrate will get recombined with the holes, and the extra holes will create the channel, that is the P channel, because the channel is created due to holes, so it will be a P channel. And since the substrate is of N type and our channel is formed of P type, that is P channel, this channel is also known as inversion layer. So we can write here that since substrate is of N type and channel is of P type, it is called inversion layer. So this will happen when our VGS is negative but it is not less in magnitude. So after a certain negative VGS it will happen. Like when we applied VGS negative but which was less in magnitude, channel didn't form. But when we increased the VGS in the negative direction, that is we made our VGS more and more negative, our channel got formed and we have a P channel. So after a certain VGS, that VGS is known as threshold voltage and we denote it with VTP. Here T is for threshold, P is for PMOS and V is for voltage. So this is the threshold voltage of PMOS. So we can write here in the fifth condition that our VGS is not only negative, it is less than VTP. And why we are writing that it is less than VTP? because we are increasing the VGS in the negative direction, not in the positive direction. So it should be less than VTP. Like this. If this is VGS, this is ID, and if we increase our VGS in the negative direction, so up to this, let it be VTP. After VTP, if we increase the VGS in the negative direction, our current will increase like this. So for these value of VGS, we are getting the current, and these values are less than VTP. We can clearly see from this graph. So we are writing a VGS is negative, less than VTP, and VDS is negative, then we are getting the current. Now we will see the sixth condition. So our sixth condition is that obviously VGS is less than VTP and VDS is negative, but it is increasing in negative direction. That is, we are making our VDS more and more negative. So what will happen? After a certain VDS, our channel will be depleted of holes even after having strong electric field. Current won't increase, it will saturate. So here we are applying negative voltage at VDS. We will have electric field here in this direction, and if we keep on increasing this negative voltage, our electric field will be getting stronger. But after certain VDS value, our this channel will be so depleted of holes that even after having strong electric field, current won't be able to increase because there won't be much holes left in the channel. So it will just saturate, and we can see its graph like curve of ID versus VDS. That is, up to a certain VDS, our current increases, and then after a certain VDS, our current gets saturated. So this is VDS sat, and this is ID sat. Now let us see one more thing, that we got the ID versus VGS curve like this. If we draw ID versus VSG curve, we will get curve like this, and this will be our mod of VTP. So we just flip the terminal. Here we are using VGS and here we are writing VSG. So our curve will be like this, and this VTP will be here mod of VTP because VTP is negative. So here if we are writing like this, we have to take mod of VTP because mod of VTP will be positive and VTP is negative. And we can see that it is same as the curve for ID versus VGS for NMOS, because in NMOS we saw that our curve is VGS and this is ID and this is like this, and this was VTN. So the only difference in this is for NMOS and this is for PMOS. So the only difference in these two graphs, you can see that we have, instead of writing VTN, we are writing mod of VTP, and instead of writing VGS, we are writing here VSG. Now, if we look at the curve of ID versus VDS, so this was our ID versus VDS curve. And this is VDS set. So if we draw the curve for ID versus VSD, we will get this. And this is our VSD sat. And it is also same as the curve of ID versus VDS for NMOS. So the only difference in these two curves is that we are using here VDS and here we are using VSD. So we can say one thing, that for NMOS and PMOS, here if we write VGS, we can write here VSG. For VDS, we will take VSD. For VTN, we will take VTP, that mod of VTP. And for cutoff region, VGS is less than VTN. And here we will take VSG greater than mod of VTP. And for linear region, we will take here VGS greater than VTN. And here we will take VSG greater than mod of VTP. And 0 and this. So for the linear region, we had the condition for NMOS that VGS should be greater than VTN and VDS should lie between 0 and VGS minus VTN. And for PMOS, we will have the condition that VSG should be greater than mod of VTP, and also our VSD should lie between 0 and VSG minus mod of VTP. And for saturation region, our VGS should be greater than equal to VTN and VDS should be greater than equal to VGS minus VTN. And in PMOS, VSG should be greater than equal to mod of VTP and VSD should be greater than equal to VSG minus VTN. So instead of VGS, we are using here VSG, instead of VDS, we are using here VSD, and instead of VTN, we are using here mod of VTP, and the rest equations are same. So now let's see the current equation for PMOS. First we will see for linear region. So in linear region, our current equation will be ID equals to mu p COX W upon L VSG minus mod of VTP into VSD minus VSD square upon 2. And here mu p is the mobility of holes, because in PMOS our charge carriers are holes, so we are taking the mobility of holes. COX is the capacitance of oxide layer. W is the width of channel. L is length of channel. Mod of VTP is threshold value or threshold voltage of PMOS. And we can write here that magnitude of threshold voltage, because our threshold voltage is just VTP, which will be negative in magnitude, but here we are taking the mod, so we are just taking the magnitude, that is, we are not taking negative or positive, we are just taking the magnitude, the value of threshold voltage. Now we will see the current equation for PMOS for saturation region. So for saturation region, we know that our VSD should be greater than equal to VSG minus mod of VTP. So in place of VSD, we will just put VSG minus mod of VTP in the current equation of linear region. So after putting that, we will get mu p COX W upon L, and here it was VSG minus mod of VTP, and we had here VSD, so we will write here VSG minus mod of VTP, and then minus VSG minus mod of VTP whole square upon 2. So we will get here, multiplying these two, we will get the square minus VSG minus mod of VTP square upon 2, and after solving this, we will get the half of this. We will get this VSG minus mod of VTP square upon 2. So this is the equation of current for saturation region for PMOS. After this, we will see in the next video, and this is it for today. Thank you.